A well-established theme of computer science is the usefulness of having multiple representations of your data and being able to transform between them. In linear algebra, the analogous thing is change of basis. So suppose we have a basis A1 through AN for some vector space, big V. How do we go from a vector B in big V to the coordinate representation U of B in terms of A1 through AN? We saw before that by the linear combinations definition of matrix vector multiplication, the coordinate representation satisfies this equation. The matrix, whose columns are the basis vectors, times the coordinate representation equals the original vector B. We now know by the unique representation lemma that U is the only solution to the matrix vector equation A times X equals B, where A is the matrix with A1 through AN in its columns. So we can obtain the coordinate representation by using a matrix vector equation solver. Let's define the function that maps from f to the n to the vector space big V by f of x equals this matrix times the vector x. Now this function is onto because A1 through AN are generators for the codomain. It's also one-to-one by the unique representation lemma. So this function is an invertible function. Now let's consider two bases for the same vector space, A1 through AN and C1 through CK. We define the corresponding functions. F of x is this matrix times x. G of y is this matrix times y. Then both f and g are invertible functions by the argument we just gave. Now consider the function f inverse composed with g. This function maps from the coordinate representation of a vector in terms of C1 through CK to the coordinate representation of the same vector in terms of A1 through AN. Now here's a very important special case where the vector space big V is f to the m for some m. In that case, the fact that f is invertible implies that this matrix is an invertible matrix. Similarly, the fact that G is invertible implies that this matrix is an invertible matrix. Putting these together, the function f inverse composed with G has this property, that applying f inverse composed with G to a vector x is the same as multiplying the vector x first by this matrix, whose columns are C1 through CK, and then by this matrix, the inverse of the matrix whose columns are A1 through AN. So we see that if A1 through AN and C1 through CK are both bases for f to the m, then multiplication by this matrix maps from the representation of a vector with respect to C1 through CK to the representation of that same vector with respect to A1 through AN. We can conclude that given two bases of f to the m, there is some matrix B such that multiplication by B converts from the coordinate representation with respect to one basis to the coordinate representation of the same vector with respect to the other basis. Now, converting between a vector and its representation can be seen as a special case of this process, where we think of the vector itself as just the coordinate representation of the vector in terms of the standard basis. Here's an example. We want to map from the coordinate representation with respect to these vectors to the coordinate representation with respect to these vectors. We use this matrix. It's the product of the inverse of the matrix whose columns are the new bases times the matrix whose columns are the old bases. Now this inverse is this matrix, so this product is this matrix.